and the Everett interpretation is correct, I exist in many different branches of the wave function. Okay, in one I got invited to this meeting, and in another one I didn't. So if I know the full wave function, and I want to know what's going to be the first question after this talk, I need to know what branch I'm in. Okay, that's not something, it doesn't say anywhere in the full wave function because it has both. So I need to know, I need to condition on what I actually know about my location, both in 3D space and in Hilbert space, to get the right density matrix to work with. On the other hand, it also isn't necessary for me to know the state of everything to predict what's going to happen tomorrow. For example, I can safely ignore everything about the Andromeda galaxy for tomorrow, because what's happening there right now is going to take 3 million years to have an influence on Earth. Right? All that's relevant is stuff that's nearby, and I can do the operation known as partial tracing to just get rid of all that irrelevant information. That's why, in fact, we can, with our small brains, do so much useful physics, because we don't need all the information about the world to make predictions about it. That's why we can make predictions for things which are much bigger than us. Okay? So we all have our personal density matrix, which is related to the full quantum state by doing two separate things. You do conditioning, like in classical Bayes theorem, folding in information you already know, and then you also marginalize in classical physics, or partial trace, as we call it in quantum geek speak, over the stuff that you don't need to know. Okay? So the true picture, the way to think about our universe is that really we start out in some weird quantum fuzz, the particles are in a superposition of different places, and then you evolve into a superposition of many different classical universes. We're in this one maybe where the galaxies are organized the way we actually photograph them. The entropy of the whole thing is completely irrelevant for us. The entropy of the full quantum state could be zero at the particular state. What matters is if you know that you're on this particular branch, and you then what? And you partial trace other things you don't care about, then what's the entropy? That's what we actually measure when we talk. So we should avoid loose talk about the quantum density matrix or the entropy. All right? So what can we do about this then? Having said that, there are some very specific mathematical recipes. There are three closed recipes for all of physics. Closed recipe one is what we all learned in kindergarten or grad school or whatever when we first took quantum mechanics. The object is not it's just interacting with itself. Then we use unitary evolution, solve the Schrödinger equation, figure out what's going to happen. Okay? For example, as we saw yesterday, if you put an object like a car balanced exactly like this, it'll fall down in a superposition of two different places. It's an example of where entropy does not change. You start with being in a definite quantum state. Now you're actually in when and causing the environment to learn information about what the object is doing. Okay? And it was famously shown first by Dietrich Say, and then pioneered by a lot of nice work, Wojtek Zurek and many others. What that does is it takes this density matrix and exactly gets rid of these off-diagonal elements, basically changing and into or. Now it's here and there, and now it's here or there. Effectively, two places at once. We can think of things as having branches, as Simon said, even though, of course, there's still just one wave function. Okay? That's what ecoherence does. I'm not going to bore you with all the math here, because you can read about that elsewhere if you want to. But the bottom line is with only one page of math, you can derive this very simple result that these magic off-diagonal numbers, which sort of distinguish between quantum superpositions and just classical ignorance, can be made to go away. The key thing about this is it doesn't say anything about what kind of system it was that involved in this math that interacted with the object. I, in this calculation, used the symbol smiley face and sad face for the system that was kind of observed in the object, just to make you think that it's a person looking. With the math this leads to a very simple answer to the question of what counts as an observer, actually. Now, do you need to be a human or a mouse or a robot, or does it suffice with a photon? Einstein wondered about whether a mouse looking at the moon would actually, affect it. We now have a very simple answer to this, which is all of the above count as having these effects. What matters isn't whether you're conscious or not. What matters is just the transfer of information. If you have something which is both here and here at the same time, for decoherence to take place, it'll work just fine if for example, Simon Saunders comes out and up and looks at it and then walks away. But it'll work equally well if just one particle of light comes in and bounces off of it, and bounces away. Because now, where that particle of light is going to be a little bit later will depend on where it was, right? So by looking at where the photon is, you can figure out where the remote control was. The information has leaked out. You can think of, in a way, keeping quantum mechanical being all about keeping things secret. As soon as the information about what's going on leaks out anywhere else, whether it be encoded in a human brain or in the position of the photon, you're no longer going to be able to measure any interesting quantum behavior there. All right? Let me just say a couple of other quick things about decoherence also, because I want to just make clear this is not just something very philosophical. It's something very practical. You can calculate all sorts of things with. First of all, decoherence is actually the fastest process in nature by a huge amount. Okay? And just to appreciate that a little bit, suppose I take a cup of coffee from outside and I drop a sugar cube into it. And I think of my sugar cube as system one, the object, and the coffee is the environment. There are going to be this is going to interact with the coffee as it hits it, right? There are going to be several things happening. There's going to be some dissipation, where some of the energy of the sugar gets dumped into the coffee. It's going to slow down. And also brown motion, if you look really carefully on the sugar from the random motions of the molecules in the coffee. There will also be communication, whereby information is transferred. So there will be information in the coffee about exactly where the sugar fell from the waves in the coffee, right? And as a result of the information transfer, there will be decoherence. And for each of these four kinds of processes, you can write down a time scale. How long time typically does it take for this thing to happen?